scattered in.
Well, it's my pleasure tonight to introduce Phil Whiffin,
5 buildings.
who, as you can see, is the Programme Manager for Advanced Propulsion Systems here at the WMG. He has a background going back to the beginnings of automotive electrification, working for JLR, and then with JCB as Chief Electrical Engineer, developing, I believe, an electric digger.
Yes, just launched.
Yeah,
Yeah.
that'd be a bit quieter, I expect. And what we're hoping to do tonight is to learn from his experience about the problems encountered in automotive electrification and see what application there will be in the marine sector. As many of you will know that in Scandinavia there are already quite a number of hybrid electrical propulsion systems for ferries. Of course, they're much more sensitive about pollution and problems of that nature, which is one of the big downsides of diesel propulsion. So they've gone ahead with these hybrid systems, which are being introduced in this country. Scotland, I think, have just produced, Ferguson's have just built one, haven't they, for a ferry system in Scotland. But there are lots of places where it would be a good idea to do something of that nature. Portsmouth being, as some of us know, a prime candidate. So without further ado, Phil, please take it from there, and thank you very much for coming and for doing this presentation.
Yes, so thank you. So yeah, my background, 22 years at Jaguar Land Rover, finishing up doing a lot of electrification. Got the scars to prove that and some of the lessons learned. A little stint in rail and then a few years at JCB. So a few different sectors. I haven't ever had anything to do with marine, so this is going to be interesting. But I think some of the issues that we encountered apply. And I think, I think engineering is engineering, to be honest. So, you can't change the laws of physics. So, it's a Star Trek quote, I think, that one. So, what I wanted to do is start talking about why cars are going electric. What's that? What are the reasons for that? What can we learn from that and carry over to marine? And then why, should marine go electric? Is there a driving force? Are there other things that it should be doing? And then I'll talk through basically 3 different case studies and apply some of the learning from automotive to those. Then we'll revisit and go back to the key lessons from automotive and see did they apply, did they not apply? Talk about a few potential marine applications and then some questions. So fairly informal. I'll try and go through it and probably keep questions to the end, but if there is something that you really think, stop me at the time if it's absolutely the right thing to do as we get through the slides. So, why is automotive going electric? Well, the obvious one is the climate change and air quality. You see that everywhere, and I think air quality, as much as climate change these days, it won't be too long before about 70% of people live in a city, and that's when air quality becomes really important. Local air quality, as much as, and I think it'll be as important as climate change. So moving the emissions out of the city is quite important. There's always the issue of where does the electricity come from. When it's clean, whether it's dirty, whether, coal-fired power stations, nuclear, whatever, or renewable. But what electricity allows you to do is move the emissions, even if they're not quite as clean as you might hope. But you do get zero tailpipe emissions, which is the key thing. Energy security is another reason. I think peak oil's been talked about for years and years and years, but it never quite seems to happen. But obviously we've fought a number of wars over the last few years, been involved in a few wars because certain countries have access to oil which we want to keep that access going, really. So protecting ourselves from that is one of the key reasons. Consumer demand. You might hear of CASE or ACEs spoken about, and these are what they call the 4 big mega trends in automotive. So C is connected, so connected cars, streaming data backwards and forwards. A, autonomous vehicles. S for shared, so the ownership profile has been talked about being changed, and then electrification. And again, electrification driven a lot by the needs for air quality, etc. And then finally, I've put a chicken and egg there because which comes first? It's always a good question. But in the UK at the moment, we make about 2.7 million diesel engines, and we export half of those. And if that was to stop, and we don't replace that with anything else, we'd have an issue with balance of trade. And the other issue, of course, is that the electrification components are actually a lot more expensive than the engine components they might be replacing. So unless we start and we get involved in the supply chain for those.
Okay, thanks, Phil. Okay. I'll be alright if I have to change my crutch over.
Okay.
Thanks. Sorry about that.
Don't worry.
Sit there.
Thanks.
So we need to do it to protect balance of trade, but also it's a growing market. They're high value items. Getting involved in the production of those is actually a big market opportunity. So that's also driving it. But as I say, it's a bit of a chicken and egg. So automotive electrification. It isn't all jumping straight into an electric car. There's steps. So if you take a conventional car, it has, say, a 100 kilowatt engine which does all the propulsion. It does actually have a motor on it, an electric motor for stopping and starting the engine, and a small battery which is used to support some small loads and lights, etc. Some of the ancillaries. Then you can move up to a mild hybrid where you might be able to slightly downsize the engine, and then your motor just gives you a bit of torque boost, whatever, might be a bit of extra acceleration, or you might actually use it to downsize the engine and use it to maintain the same level of power. Of course, you need a slightly bigger battery because it's doing more work, there's more power and energy needed. As you move to a full hybrid, your engine's got a little bit smaller possibly, your electric motor's got bigger, and also because you're doing more work again with it on the electric side, you need a bigger battery. There are many different types of full hybrid. You could have a series hybrid where effectively the engine is just a generator connected to an electric motor as a generator, and there's no mechanical connection between the engine and the wheels. You use another electric motor to give you propulsion. Or a parallel hybrid where either the motor, the electric motor, or the internal combustion engine can drive the wheels independently, together, or both at the same time. There's obvious advantages and disadvantages of both depending on the duty cycle. A plug-in hybrid, the aim of a plug-in hybrid is to give you a little bit of electric-only range. It's plug-in because you would effectively be able to charge the battery up at home before you left, which means you need a bigger battery. You don't necessarily need a bigger electric motor, but you might be able to do 20 or 30 miles maybe of electric only. the new London taxis are plug-in hybrids, and the idea there is that when they're running outside the emission zone, they can run as a hybrid, and when they go inside they're supposed to switch over and run as zero emission electric only. Sounds great, but in many ways they could, in order to get the battery charged and running before they go into the ingestion zone, they could actually be running the engine a lot more and creating bigger emissions outside. So, you know, it's all swings and roundabouts. A REEV's something a little bit different. So this is range extended electric vehicle. So effectively this is an electric vehicle. An i3 is a good example of this. So most i3s you can buy as a BMW i3, you can buy as a full electric, but you can also buy a little range extender, which is a tiny little engine that sits in the boot. And it's there for when you run out of electric energy, you still want to get home, it gets that panic away, and it acts as an auxiliary power unit. In most cases, with a REEV, that auxiliary power unit is designed to be there for only emergencies only. So actually, an i3 that's running off the engine, when the engine's running, will not have the same power output. It can't maintain the same power, so your cruising speed on a motorway would be lower. And then an electric-only solution, which is fully electric. There's an interesting thing, we'll come to it in a few minutes when we talk about costs in an electric car. The most expensive component is the battery. If you've got a full EV, you're probably going to be scared to use that full capacity of the battery. The most expensive part of the car, because if you get stranded away from a charge point, you're actually not going to use that full battery. It's the most expensive bit. If you've got a REEV with a range extender, you possibly will use that full range, so you're utilising the most expensive component on the car. So again, you know, there's some things to think about as to what's the right thing for your customers. So as I say, as I touched on it, the battery in a electric, particularly a fully electric car, is an absolutely defining component. So it's effectively the fuel tank. So the battery defines how much energy, the size of the battery defines how much energy you've got, which defines your range. The energy density in even with the best lithium-ion batteries is about 40 times worse than diesel. So you're never going to be able to get as much energy in as you can with fossil fuels. Fossil fuels are fantastically energy dense. The other thing about fossil fuels is you can get them into your tank very quickly. So charging a battery will take more time. And even with some of the big high-power superchargers that you see with Teslas, they have to be cooled. If the two people show up at the same time at a Tesla supercharger station, then both cars charging twice the time because it can only supply so many kilowatts. The other thing about the battery is it also defines the power, if you like, the performance of the car. So how quickly you can get that energy in and out. If you look at the analogy I've mentioned here, it's a bit like the size of your fuel pump. If the fuel can't be pumped out quickly enough, it's going to limit your performance. Batteries also a massive weight in the car, so where you package it will affect the handling of the car. We've mentioned range, cost we're going to come to. Where it's packaged in the car will affect the way the car drives and handles. And it probably defines the life of the car. So as the battery ages and as the range goes down, it's going to cause your car to be devalued over time as well. So it really does define the vehicle. Batteries don't like to get too hot and cold either. They won't accept charge when they're outside of that range. You'll damage them. So you actually have to heat and cool them. And I've already mentioned talking about charging. If you have a really massive battery, that's great, but if it's going to take 16 hours to charge, that might be a limiting factor. So, again, looking at these different types of hybrids against the conventional vehicle. So at the top here, we've got a conventional powertrain. I think it's showing up there as, let's say, £16,000. And as we come down and get into a fully electric vehicle, you can see the cost of the battery just wipes everything out. Absolutely wipes everything out. Interestingly, all the other types of vehicle apart from an EV still have to have a conventional powertrain as well. The reason there, so you end up paying double, if you like, because you've got two sources of propulsion. But the reason they end up being cheaper than a full EV is just because the battery cost is less, because you're not trying to deliver the full range with just the battery. But this is even after battery costs have fallen dramatically over the last few years. So, in the last 8 years, the battery cost has come down fourfold. If I was to show you a graph, it's one of these graphs that's curving down, so we've got an asymptote, so it is starting to level out, and it will always be fairly high. Even as the volumes go up, even if we get to figures such as $100 per kilowatt hour, it'll still be a massive, significant cost. So, where are my scars then? So, first thing you've got to do, and again, you've seen products that have been launched and they've made these mistakes, and the product's failed in automotive. If you don't understand your customers, they won't buy the car. And what will stop them buying the product? The classic one everybody talks about is range anxiety. They're worried that they won't be able to plug in and charge. They'll get stranded by the side of the road. So that will put them off buying it. But there's other things. The way the car operates might irritate them. It might not have the same top speed. It might be an issue that it's silent. There's rules coming in about putting noise generators on these cars around car parks so that people can hear them coming, so they don't accidentally step out in front of them. But there's things you have to understand what the customer's going to do with it and what concerns them. And then, as you do that, in order to size the electric components, and because they define the performance, etc., you've got to know the duty cycle. You've got to know how much power and energy this is going to consume. You need to know how often they need that power and energy. You've got to understand these. If you don't understand that, you will not size the product correctly. The thing about combustion engines is they're really, really flexible. The same car that I can drive around a city in, I could get in tomorrow and drive to the south of France. It wouldn't be an issue. With an electric vehicle, car designed for the city, probably won't work on a motorway, probably won't make it to the south of France. It's a much more focused product, so you have to get it right. Point 3 though is you can build electrification over time. So we've talked about mild hybrids, full hybrids, full electric vehicles. You don't have to jump all the way. There's a lot of learning you can do. Let's take an example of that. If you start to electrify, so there's quite a lot of mild hybrids out there. Toyota started out with effectively it's a power split hybrid, but they launched that, they learned from that, then they did the plug-in, and now electric vehicles are starting to come in If you jump straight in, it's expensive, and if you get it wrong, you can get problems. Start with the right application. There are some duty cycles and applications that naturally are easier to electrify. So I mentioned a city car, smaller city car. So smaller city car probably doesn't have to travel very far. So you might travel 5, 10, 15 miles to work every day. So they don't need much energy. The other thing is it's not on a motorway, so it's not pushing through all this air resistance. So it actually doesn't need as much power. So it's not just lower energy, it's lower power as well. So it's easier to implement, so a cheaper battery. Mentioned here, there's a reason why you don't see electric lorries yet. Because you start to do the calculations and you find out you lose half your cargo capacity with a massive battery. You know, you hear talk about some of these lorries perhaps having things like bumper cars so they can actually charge as they go along, because carrying the weight of that battery makes them quite inefficient. It's a lot of load space. Predictable duty cycles are good for electrification. If you always know that you're going to travel 5 miles, you can size the battery exactly for that. And what's more predictable than a bus route, for instance? You can work out a bus route, you know where it's going to stop, you know it probably travels at the same speed. So buses are good. And you also know where you can charge. They tend not to drive off and go into the countryside, tend to follow their routes. And last point there, don't forget about the charging infrastructure. If you can't charge it, it's completely useless. That can be, you can turn that the other way around as well, that you don't need to go to a fuel station. I always used to hate having to veer off when I was on my way home, because it'd take me 10 more minutes to veer off, fill up the fuel and then go home when my car was running out. If I could drive home and plug in at home, actually that saves me time, and never having to visit a fuel station, that'd be great for me. I'd be happy, because filling up with fuel is always a distress purchase. It's not something you ever choose to do, it's something you have to veer off and do. But in the end, in automotive, you know, no matter how good the product is, it's actually being driven by external intervention and legislation. And that's going to come more and more, particularly with zero emission zones in cities, you know, talking about banning diesels, tax breaks. That's really, that market intervention is what's giving this kick to the take-up. So, I'm going to talk a bit about marine now, which I'm sure you. So, why would you want to do electrification in marine? Well, it's actually a lot of the same reasons. This graph on the your right, my left, is quite interesting. So this is CO2 emissions by sector. You can see road is down there, sort of bottom right quadrant, fairly big percentage, and then you've got aviation and shipping, both around 2 or 3% in orange at the top. So not as big, which is quite surprising really, but still sizable. But the interesting thing is it's quite difficult to do anything about them. Cargo ships, they're out in international waters. How would you control with legislation? How would you control that with legislation? You know, it's easy for a city to bring in emission rules, or a country to bring in emission rules, but that actually, aviation and shipping are two that need a lot of cooperation around the world, so it's a little bit more challenging. But as I say, that's about 1,000 million tonnes of CO2 annually. Imagine it's difficult to control, and if we do try and do something about it, it's going to affect the cost of the goods, because if we affect the cost of the shipping, you're going to affect the cost of the goods. potentially drive up inflation. So it is challenging. We all like our cheap goods from China or wherever. But you know, it's spread out around the world in the oceans, that emissions. But at ports is where it's pinch point. Those ships are all coming into one port. Not only have you got the ships all coming in, you've got to load and unload those ships, and then you've got all the road transport coming in there. So you've got a small area where there's lots of emissions. So perhaps there's something to be done there. Perhaps that's an area to concentrate on. And there's this survey that reckons that globally emissions around ports, so this is local air quality rather than CO2 and global warming, but is responsible for about 60,000 premature deaths annually. Energy security applies as much to marine as automotive, you know. And then we've kind of talked about cargo, but at the other end of the scale, we've got little pleasure boats and things like that, and they often operate in quite sensitive areas, in national parks and things like that. So a clean, silent pleasure boat could have some quite obvious advantages. So I'm going to look at some marine use cases now, see which ones make sense, which ones don't. I've done a lot of this based on basic assumptions of fuel costs. You can play with the numbers a bit. In a lot of cases it won't make a big difference to the conclusion, but in some cases it will. I'm not a marine expert, so go easy on me. But then again, I might be asking some stupid questions which might be good questions. I don't know. So first one, we talked about container ship. So large container ship, 8,000 TEU. I've got some figures. Consumes about 225 tonnes of fuel a day, going at 24 knots. It'll consume less if it goes slower, but it's a reasonable figure to take. And then having a look at the cost of fuel. Again, you can play around with these numbers a little bit, but at £310 per tonne for marine diesel, that's approximately, interestingly, £70,000 a day. That sounds a big number to me, but I don't know how long these ships are at sea for when they're going around the world, but I'd assume it's weeks, if not months, with cases, so that's a huge cost. So quite an opportunity there. 70,000 sounds a lot, but I'm going to make that sound a small amount in a second. So, working out how many kilowatt hours of energy are in that 225 tonnes of fuel gives you nearly 3 million kilowatt hours of energy. Now, I've tried to be fair to the electrification solution here and assumed that it's 95% efficient and taken a marine engine as 50% efficient. I know you can play with these figures a little bit. So that means we'd only need about half the energy, source energy, to give us the same amount of propulsion, hopefully. But that's still 1.5 million kilowatt hours of energy. So, assuming the cost of £250 per kilowatt hour, the battery would cost £377 million for that one. That's not the electricity in the battery, that's just the battery. But that's the cost of the fuel tank. So we've not even charged it. So it's not even worth considering that, and it's not worth considering that for a voyage. And even if you try to look at being more efficient with speed, you could probably find a sweet spot. But obviously, the longer your voyage takes, it's going to take more energy. So you've got to balance that. But what if costs were no problem? Well, the mass of that battery would be 1,100 tonnes. Where the hell would you charge that? And how long would that take? Because that's, that's 1.5 million kilowatt hours. So it's just huge. It's not going to happen. So it's fairly clear that's not feasible at the moment. But there are things that we could do. Could you potentially electrify the ship at ports, or send out some electric tugs to bring it in and out to keep the local air quality around ports, improve the local air quality around ports? There's maybe some general efficiency changes to the existing fleet, so it'd still be an internal combustion engine propulsion system, but you can do some tweaks with electrification, maybe to put the engine in a different operating point. But to be honest, marine engines such as this are operated pretty damn efficiently, and they sit at their nice operating point. I mentioned hydrogen, an alternative fuel source. Obviously, you can burn hydrogen and reduce emissions, but again, you've got to get that hydrogen on the ship. You've got to manage it. You can run internal combustion engines on hydrogen, or you can have massive fuel cells, but again, they'd be expensive. And then perhaps using the electrical support for some non-propulsion loads as a way of increasing efficiency. Because I guess, if you could get 5-10% efficiency, that's 5 to 10% less fuel, 5 to 10% less emissions. So it's worth doing. Now you might recognise that. I think some of you might have mentioned this at the start. So that's the Norled ferry in Norway, which is an electric ferry. So let's look at the ferry. It's a bit like a bus. It's got a lovely defined duty cycle. So depending on the length of the crossing, you know exactly how much energy it needs to get across, and you know when you can charge it. You've probably got a reasonable amount of time to charge it when it's sitting being loaded. So again, I've used this sort of similar approach. So a large RoPax ferry uses about 1.3 tonnes of fuel per hour, so that's cost of about £400 per hour, and that equates to 17,000 kilowatt hours of energy per hour. Slightly different figures because these are per hour, not per day, as the other ones were. So. But they're still orders of magnitude different. Again, taking the efficiency of the electric drive line, we probably only need about 8,600 kilowatt hours per hour for this vessel. So the battery costs will last 1 hour, so if we had a crossing of an hour, we might give ourselves a bit of extra battery capacity so that we don't, if we're stuck at sea or if we're, working against tide or whatever, we're still safe, we're not going to run out of power. Let's make it a 10,000 kilowatt hour battery, so that's 2.5 million. Now on a ferry cost of about 35 million, we understand these things cost. That's not impossible. It's expensive but not impossible. Mass of battery 7.3 tonnes, so that's feasible. But you still have to look at the cost. The running cost in this situation. So extra fuel costs about £400 per hour. The cost to make this feasible will have to be less than £400 per hour. So that's about 4.5 pence per kilowatt hour. So these are UK costs, about 8p for solar, onshore wind 5p, nuclear can be as low as 2.5. So yeah, depends where your energy is coming from. Norway, where this ferry is running, they've got loads of hydro power and very, very cheap electricity, and not only cheap, very, very green electricity. So it would make a lot of sense. If you've only got access to very expensive electricity, your running costs aren't going to be any cheaper. So even here, we cannot justify on cost alone necessarily. But local air quality, emissions, Norway has already pushing this. This ferry's been in service since 2015. They've got 1 megawatt hour battery on board. It's a shorter crossing than the one I've looked at. But in order to do that, they need charging infrastructure. Interestingly, the grid can't support the charging, so what they've had to do is they've got a battery, a large battery at either end where it docks, which charges slowly from the grid, not when I say slowly, as quick as it can, whilst the ferry's at sea, so that when the ferry docks, they then effectively transfer the energy out of the battery that's on the shore into the battery on the ship, supported by the grid, because the grid infrastructure wouldn't be able to charge the battery on the ship fast enough. They'd have to wait around. So it's effectively 3 large batteries. So you have to cost that in as well. Then pleasure boats. So get it down here, it's easier. I won't get a crickle on it. Pleasure boats. Well, it's really difficult to do a single use case for a pleasure boat, because pleasure boat is a million different things. But there's already lots of electrified pleasure boats out there, so it's clearly possible. Over 100 companies looking at some of the forums for electrified boats that are there. So as I say, there's clearly a business case. So I've pulled up three very different products actually. First one is this Silent 80, which is a very expensive, they call it a yacht. It's not what I'd call a yacht, but it's a floating hotel. Really. So that's about €4.5 million. It can chug around at about 20 plus knots, but I don't think it'd be able to do 20 knots for very long before it's emptied that absolutely massive 250 kilowatt hour battery. And you can have that. It comes with 280 kilowatt motors, or you can pay the extra, and I think actually to get the 20 knots you need these 250 kilowatt motors. So I think you can see that if you were to run it flat out with those 250 kilowatt motors, you'd empty that battery in half an hour. That's assuming that it's 100% efficient. In fact, what I think that you can see, it's got all these solar cells on the roof. I think what the boat's really about is you sail slowly to somewhere more up in your nice bay, and the solar cells will operate all the what are called hotel loads while you're there and keep that running. They're not really there to charge the battery, because they just wouldn't. It would take weeks. But it'll operate the electrical system on the boat, so you're not depleting the battery. Then there's this Aqua 848. What would you call that? Is that a speedboat of some sort? But again, that again, they say 22 knots, but actually you wouldn't be able to go very long at 22 knots before you've depleted the battery. 16 kilowatt hour, you can pay extra another 32 kilowatt hour battery. That's about £300,000 or euros, I think that is. So not cheap. And then there's this Reuben Ace, which is, I think, representative of a lot. There's a whole host of product around this sort of size, which effectively is a small boat with an electric motor on it. quite convenient if you want to go fishing and things like that, I think. Probably a very, what I call a low duty cycle, not high power, not high energy. Could actually be quite convenient. I don't know if you're the kind of person who has a mooring at the end of your garden, you can charge your boat up by plugging it into your house electricity. That's actually quite convenient, isn't it? More than sort of taking jerry cans of fuel down to it and things like that. So it's probably an advantage. So, you know, there's lots of different products, so there clearly is a market. But again, if you get the duty cycle wrong, you get stranded. So you need to be careful. Advantages, well, they're clean, quiet, they can be simple to fuel. They can be lower maintenance. We see that a lot in automotive, and that can be an issue actually for the dealers, that they don't get to see the cars as often, because when you take your car into the dealer, they make some money. If they're not seeing the cars, the dealership perhaps not making any money. And if the dealerships aren't there, there's nobody to sell your cars, so you won't sell new cars. So you do have to keep the dealers going. But you know, these smaller boats, you could easily stick a backup outboard motor on for emergency. So that to me is your equivalent of a REEV, a range extending electric vehicle. So that's sort of easily doable. Disadvantages: time, the actual time to charge. Particularly, you've got these huge batteries, 250 kilowatt hour battery. That's going to take a long time to charge. The range and usage time is limited. Your speed versus range formula. If you want to go fast, you're not going to go far. If you want to go far, you're not going to be able to go fast. They can be high cost, initial purchase cost, especially. You need access to a charger. But I think there really is some good product out there. That silent 80 makes no sense to me at all. Honestly doesn't. When you look at, you know, we do some calculations on the size of your solar cells and the amount of charging versus the size of your battery. The battery's just oversized. But I think people who've got 4.5 million in their back pocket probably don't care too much. Oh God. Yeah. But so far we've only really considered full electrification. There are other things that you can do. We touched on some of these. So solar power, particularly if you've got a lot of surface area, can be good for maintaining auxiliary loads. It means perhaps you don't have to run your engine to keep as a generator, so that could be cleaner, especially if you utilise the surface area of a large ship. That might be useful. But solar energy, it's got the same issues it's got anywhere else. It's not always available if the sun goes in. You need a battery to have somewhere to put that energy, which again adds cost. And it's not good for large loads, large electrical loads. We mentioned hydrogen before, fuel cells, hydrogen. So for these really heavy duty cycle applications such as the cargo ship, electrification is just not an option. But you could consider moving to hydrogen. If it's a fuel cell approach you're taking, effectively you've got an electric ship because the fuel cell's just converting the hydrogen to electricity. So, or you could convert the engine to run on hydrogen. It's got a large energy density compared with a battery. Not quite as good as the diesel, and it helps your local emissions. You've got to create that hydrogen somewhere, and lots of ways of making hydrogen use electricity, and depending on where that electricity has come from, that can be quite dirty. But system cost and fuel cost versus ICE or internal combustion engine diesel could be not so good. and the overall efficiency is probably not as good at the end of the day. As you convert in chemical energy into electrical energy, into mechanical energy, all those conversion losses that come. Series hybrid, so just like in a car where your generator generates electricity, there's no mechanical connection between the engine and the wheels, if you like. You could do that in a ship. And the advantage of that is that can give you distributed power. If you've got challenging mechanical connections, then that can be quite nice. It can be quite modular as well, you know. Once you've got a high voltage electrical distribution system, you can just hang other things off it. It can be quite useful, and can be one way to add features and take features off. It can allow you to downsize your internal combustion engine for peak power. So you'd size your engine, if you like, for your average output, and then as you needed a bit of a boost, you could add to it with electricity, electric motor. So it allows you to run the engine at higher efficiency. But as I said, in many cases the marine engines are run at pretty much their best spot anyway, so you haven't got quite the same issue with people going up and down speeds on motorways and things like that to enable you, to give you that amount of opportunity. It can give you a short period with engine off, so you can get some zero emission running, and it can be modular. But as I said, you've got conversion losses because you're converting energy from one form to another, with very little opportunity to recover energy. It doesn't offer any opportunity to downsize your engine at steady state, its cost, and it doesn't give you any significant zero emission running. Mild hybrid, which is a small electric motor, give you a little bit of boost, so you might get some slight downsizing for peak power. It doesn't make conversion losses any worse because you've still always got that mechanical connection to the engine. It's fairly medium cost, and it's something you could retrofit. So again, that's could be your first step. But it's no good for getting any zero emission running, or any real significant engine downsizing. So, slight update to this slide then. So, does the key issues that are raised from automotive, do they apply to marine? Simple answer is yes. So you need to understand your customers and their worries. Yeah, if you don't understand your customer, you will deliver the wrong product. And as I said, electrification needs to be. It's a lot more focused on a particular application. It hasn't got that flexibility. So if you get it wrong, you get it wrong big time. You've got to understand your duty cycles just as much. They might be a bit easier to understand it. There's probably not so much interaction with traffic flow and things like that because it can affect them. But you still need to understand them. And the risk of getting it wrong are high. I mean, being stopped on the motorway on the hard shoulder is one thing, being stranded at sea and drifted into the rocks is another. Obviously you can build electrification over time, and many larger vessels already have a good degree of electrification. Small generators running for the hotel loads have enough to run all the propulsion system. Add on electric pod drives and things like that. It's there now. Start with the right application. So, two key ones for me are the short hop ferry. I think that looks good. It obviously is good because they've already done it, and lots of pleasure boats. But again, it's the right niche application. All of these would be absolutely useless if you can't charge them. So, already mentioned the ferry needed batteries put in at each of the docks to smooth out the demand on the grid. So you've got to think about that. You've got to think about where people are going to charge it. Perhaps a little bit different. In automotive, a lot of this being driven by external intervention and legislation. Perhaps isn't at the moment still that isn't the same size of driver, but you can see it happening. It's just a bit more difficult because of the international nature of, say, the cargo side of it. But locally, legislation at ports, things like that, you can see that coming in. Incidentally, when I was at JCB, I was involved in one of the electrification projects we were looking at was to do with the loading and unloading at ports, some of the material handling, because of the pressure put on some of these port authorities to bring their emissions down. So it is coming. So just about finished. But, so zero emission. It's absolutely nothing new. That was delivering. That was going all over the world. They were sailing all over the world with no demands on energy or fuel. I suppose you've got to feed the people on it. But why can't we do something like that? And there's opportunity, isn't there, really, to be honest? So that's the past. Pretty damn good, actually, I think. Today, there's a zero emission ship for you. It's nuclear powered.
Apart from the aircraft.
Yeah, actually that's true. That's actually true. Yeah.
All the waste that goes over.
Yeah. Yeah, absolutely true. But I guess submarines, some of the sort of big military. There's a fair amount of nuclear there. Yeah, and then this NYK future ship concept, sail and fuel cell. So bringing a bit of everything in to try and make it more efficient. But I think that looks a lot like that, to be honest. Particularly, I think cargo's the big problem, and that's where if we want to, but we've got to address it in a way that doesn't have lots of cost. Because if we do, then we'll all be paying more for our goods, and that's not really on at the moment. So I think that's me. Thank you.
You seem to take a fairly dim view of the prospects of increasing the energy storage density of batteries. Do you think we've reached the limit?
We've not reached the limit, but the steps that we'll get smaller. There will be some opportunities with some different chemistries. You'll get a step change and a step change. But there is I'm not a chemist, but there are fundamental limits that you can get to, and you can, what the chemists do is they look at the periodic table and they pick out the material that gives them, and then you can work out a theoretical limit of where you can get to. I'm not sure where that is, but we will start to come across that. And then, of course, then you get the other issues of even if you can meet that, you've still got to get the energy in and out, getting energy, through copper cables, etc. Electricity, there's limits to how quickly you can do that. You end up having to cool. You start coming across other mechanical issues that come into it, rather than just the fundamental chemistry. So,
the rare metals that will be necessary will also provide some sort of limit, surely.
yes, yeah.
There's lots of discussion about that on the web, about there not being enough of the right materials available.
And to be honest, we talk about CO2 produced and emissions while in operation, but an electric vehicle takes more CO2 to make in the first place as well. And that would apply here.
And taking to produce subsequent batteries for it if you extend its life.
Yeah.
Mm-hmm.
From my time at sea, I always remember, I think it's fairly obvious that most ships' engines, like you just said, are pretty efficient when you're out at sea. the issue is always import. And I think, last year when we was up in the fields, as the ship pulled out of the little dock, black smoke came out the funnel, and I thought, that looks more like when I was at sea, that did. And it's the inefficiency of the engine at that time. And I think, what you just said, Lord, about ports and about air quality, the key, I think, and the driver will be, is about creating, as we've got with cities, we'll have port limits, and I suggest the answer is that we create hybrid tug systems to get our ships out into the seaway, that they can then run at, very efficient. Because my experience, we used to run pretty efficiently. It was full ahead, and that was it. You stayed full ahead till you got to the other end. There was none of this messing about, It was fully, automated, efficient running of ships. That's where we are.
Good idea.
You're never going to better that, but building something like a hybrid tug or shunter to get our ships out into the seaway, that I think is the answer. That's where I think port authorities and the future will be for something. I would suggest a hybrid, because it's about creating a tug that's efficient. Maybe a plug-in hybrid tug is the answer, but something of that ilk. And I think that's these sort of things will come out in the wash. But that's where I would suggest that the future lies for shipping and electric drives and things like that.
If I could just comment on that, we already have this system on the Panama Canal locks. The ships are manoeuvred through with electric locomotives on the ropes.
It's interesting that to see the numbers for it, because I actually, not on particularly technical level, but I oversaw in my old job a couple of projects on hydrogen hybrids. So with Ferguson Marine actually, HIFES, which was looking at the Thames clippers, so it was and what they looked at is actually a lot of work looking at the emissions and everything on the duty cycle, and got all the data, and they were only going to use the hybrid to go into and out of docking, to accelerate and decelerate, and then when it was going along it would switch. And obviously there's the project now, Hydine, which has got a lot of press in the Highlands and Islands, which is because they've got all the excess hydrogen. It's, like you say, if you've got it there, then you'll use it. But it's really interesting seeing the numbers of why, you're not going to go fully electric on a, but as you say, it's the steady state where it's very efficient, and there's not, in the middle of the sea, there isn't the same pollution concerns. It's when you're in port that you really don't want to be chucking it all out. So it sounds like it's more of a, and they were actually thinking that they were anticipating at some point some legislation for the waterways on the Thames and things. Obviously there isn't any emissions legislation yet, but there's anticipation there would be, and then they'll need to do something the same as
There was an article published yesterday by a manufacturer who stated that the hydrogen fuel cells are the answer with electric propulsion drive, and diesels will disappear, so maybe that's the way it's going to go.
Well, people have been saying that for about 40 years so far, and it ain't come right yet. If you look at where fuel cells are used, they're used for spacecraft and defence purposes. There's a clue there in terms of how much the customer's prepared to spend. The fact that they have platinum catalysting gives you some clue.
There is a company, just going to shift if I can. There is a company called Agreement International that collaborates with Barak, which is the biggest PEM fuel cell manufacturer in the world, and ABB, and they are developing a hybrid system fuel cell and a battery system. So these easy to play the future.
How is the talking your automotive batteries in an all-electric car, how is the life of the battery affected by the fast charging or slow charging, or ending up on the hard shoulder with it flat?
Well, the battery will have a battery management system which will look after it. So when we first launched them, there was no data, so we were quite pessimistic. So we weren't using the full capacity of the battery. But actually, as more data's come in, and we've learned more, they're coping better than we thought. So one of the issues, the new Leaf, for instance, it's got a fast charge capability. They've had complaints with their customers because it'll only let you charge it fast once per day, and they thought they could do it several times. So they get to their coffee stop halfway down the motorway and they find that they've only got the slow charge. But that's there to protect the battery, and it will protect it. Which is why you've got to understand your customers, but also your customers got to understand the product because it behaves differently. If I give you an example of a classic target on a car, a performance target, is a 0-60 time. Now in a diesel or petrol, you do 0-60, you can stop, you can do that 0-60 again, you can repeat it, you can repeat it. With an electric car, you can't, because as the motor and the battery's got hot, it's not capable, it needs time to cool down. So we have to set different targets. We'd have to say, right, we need to do that 0-60 time and we need to be able to do it 5 times on the trot, and then it's got half an hour to cool down. But the behaviour's different. But the battery will look after itself. The big things batteries don't like is being left charged, fully charged. They like to be kept at a level just below that. But the battery management system will look after that. If you left it plugged in at home, it would manage that and stop the battery getting damaged.
And supplementary to that, can you, if the battery were to fail, and the kind your picture at the beginning showed the whole of the floor pan as battery, are they changeable? Or is the car scrap?
They are changeable. You just wouldn't want to pay for it. So, Tesla, they're, everybody thinks they're a nice, friendly company. If you were to go on holiday and not plug your battery in, it can't do its cell balancing. It needs to be plugged in to do its cell balancing. So they don't warranty the battery if you were to go off for a month and leave the car, because it would gradually deplete over time and then it would start to damage cells. It would do that. If you leave it plugged in, it can manage that, it can sort itself out. People who didn't plug it in and then went back to Tesla to ask for them to put the car right, they just tell them to get lost. And they're left with a £20,000-30,000 bill for a new battery. And Tesla absolutely push that. They don't back down. They don't. Some of these companies will say that's the warranty situation, but as a goodwill gesture, we'll sort it out. Tesla not to. Absolutely not to.
If I could just comment on that thing, I heard a presentation last year from the head of buses in Reading. Reading have a mixed fleet of conventional buses, gas-fueled buses, and diesel-electric hybrids. The diesel-electric hybrids, the bus manager said he would scrap the fleet if he was allowed to. None of the batteries have lasted longer than 4 years. One of them only lasted 1 year in bus service, with the sort of cycles they do, and they were £40,000 per bus. He was not a happy bunny. I'm not saying that can't be improved on by battery development in future, but that's where we are now.
A lot of it depends on how much you charge them and how much you discharge them. So if you keep them between 20 and 80% charge, you're probably not really affecting the life. If you take them up to 100% or let them go down to nearly 0%, every time you do that, you're doing some damage.
It's the same with our phones, isn't it? Because chargers are smarter now. And I once had a great analogy from a guy who used to work at Ferry, and he said it's like, say, filling up a pint of beer. If you pour it in really fast, then it flows over the top, but actually it's not completely full. So it's kind of, the heads the control and the quicker charging and the not going 100%.
Could I just critique some of your comparison? I know your main interest is electrical. I really think you should have a wider range of comparators of low carbon energy systems. You've got the obvious hydrogen fuel cell one, but that's a very expensive option. There are much, much cheaper options, which are liquid biofuel and liquid biogas fuel, and that's the one everybody misses. You mentioned the Baltic running the hybrid ferries. Well, the Baltic are running much, much larger liquid gas-powered ferries than that fiddling little thing now. There are large numbers building. Now, at the moment, they're using fossil LNG, manufactured bio-SNG, which is not commercial in the UK. It is currently in Gothenburg and a few other places. I should express an interest because I spent 30 years developing SNG technology. It used to be developed at the British Gas Research Centre just 10 miles away from here. The fact that our government's ignored it is not my problem. The pathway efficiency, as we call it, from primary energy source to miles on the vessel for compressed or liquid gas, after allowing for the refrigeration for liquid or compression for gas, is about double that for liquid fuels. It's the one everybody ignores. And of course, being a gas fuel, although it's being used in a combustion engine, the exhaust emissions are actually much, much cleaner than from a diesel engine.
Yeah. Yeah.
So they're actually much more friendly for human health than biodiesel is. But you try persuading the Department for Transport that it's a viable option. At the moment, they do finally have about 80 HGV trucks running on liquid gas now, liquid biogas. They've wasted 15 years getting back to where we were in 1995 before they decided to chase after the fantasy of an electric truck. They finally agreed it's not going to happen. So the HGV and liquid gas is a perfectly credible fuel for HGV trucks for long range.
Yeah.
The energy density is slightly less than liquid fuels, but not a lot.
It comes back to that, why has electrification happened in automotive? A lot of that is down to legislation and incentives.
Indeed so.
And if the things they incentivise are happening, the things they don't.
My comment to colleagues in green energy circles is that the best replacement for a fossil fuel, is a green fuel, for the energy density reasons you've mentioned. This mania with replacing fuel with a non-fuel vector, I can never quite fathom. The easy solution is a low carbon fuel. If they didn't exist, fine, let's electrify them.
I question the idea of electric vehicles or any electrical situation. Everybody's pushing electric cars or electric vehicles of any sort, size or description. The point is, where you're going to get this electricity from to charge the bloody things? I mean, we're scrabbling around now with power stations being closed down. What's going to replace it? Solar energy or wind energy?
Yeah.
A load of rubbish.
Thank you, Alan.
We've got our head in the sand. You can't see a wood for the trees. They're not going to do it.
Something to do with the Department of Energy not having any engineers.
I'm sorry, it's not my idea.
In many ways, it's a temporary solution, particularly for cities, because then the vehicles moving around in the cities emit nothing.
No, but you're still going to charge them.
Emission has happened somewhere else.
Zero tailpipe emissions, that's important for human health.
Emissions, tailpipe emissions, but you're moving the problem. And as I said, the emissions to make them is high. You've got to operate an electric car for about 5 or 6 years to get a benefit over a non-electric car overall, including the
what, on carbon dioxide?
Yeah, but if you haven't got the electricity to charge it, what good is it? That's the question.
Well, that was on his
Nobody's
slides,
looking at the front end. Somebody to push it in. If we haven't got the power supply, you're not going to get an electric car.
Well, there's a simple answer to that, to be honest, and that's our capacity. Your power supply system is sized to meet peak, and when you're going to be charging the cars, if you manage it properly, is overnight when nothing else is on. So what it means is you're going to average out the demand on the grid. But the grid has got the capability in most cases, the generation capability. Whether you can actually get it to where you need it is another question.
Yeah, it's a generation, isn't it? You say charge them at 9. Yeah, but you're not getting any solar energy coming in. Your wind energy might be lucky if you've got enough. So you've got to rely either on nuclear power or coal. Period.
I believe that the Chinese are cornering the market and making the actual battery cells. They're making most of them, aren't they? And then you've got your battery cells, which are basically the same voltage as a mobile phone battery. Presumably and you just put hundreds of them in series. Presumably they're a bit bigger. What sort of size are the cells? And where's this? Mr. Clark, our business secretary, came to near Coventry the other day because it's place for building batteries.
UK BIC, yeah.
Where's it going to be?
By the Jaguar Whitley plant, by Coventry Airport.
Oh, there.
Yeah. So I think they might have started digging now. So that's a battery assembly. So they're not making cells there. So they'll assemble packs. But we are looking at bringing that into the UK. So it's all seen as a black art, but it isn't really. You know, there's. You know, we can make cells over the road, and a lot of the equipment that we've got over the road has come out of the food industry. There's some old VHS tape machines over there well, they're not actually VHS tape machines, but they're very similar because you're making reels and reels of material. But the mixing, etc. You know, it is difficult because you have to get it right and you have to have the process control. But it's all doable. There's no reason why we can't do it in the UK. And then you're building up that value added. There are battery plants. So there's another battery plant proposed near here called Hyperbat, which is Unipart and Williams. So there's some happening in the UK, and we will be building batteries for the UK motor industry, and I think this is what it came about with this, you know, balance of payments. You've got to offset. We need to be making stuff and exporting it, and this is the value added here. You know, from the raw materials and what you get out the other end. There's quite a nice. It's what we call high value manufacturing.
Value added,
yeah. So it's what we need to do.
Because it must be quite automated process for building the batteries. So you've got thousands of cells.
It depends. So there's 3 different formats. There's one they call pouch cells, which is effectively flat. That's like in the Nissan Leaf. So it's a flat cell with two connections on the top, and they pack them in, you know, blocks, and then you pack them in. You make up a module of several cells, and then you make your battery pack is then made up of different modules, and you connect those in series or in parallel depending on how much power and energy you need. Tesla uses cylindrical cells, which are just big version of your AAs. They're 18650s, so they're about that big, and that has thousands of those connected. Again, they go in a carrier. The Germans have gone their own way a bit, and they have what you call prismatic cells. So they build them in a particular shape, depending on the shape they need. Each cell is really like a mini module, but they're all different. As in, there's no standard. But the overall, the way to think of what's in them is all the same. You know, it's layers of material. So a pouch cell is a number. You know, you've got anode, cathode, separator, etc. in your various layers, flat. In a cylindrical cell, it's the same thing. Wrap round and round and round and round.
Swiss roll.
Yeah, exactly. Swiss roll. Brilliant. You know, there's no difference really. And your issues tend to be, you know, you're trying to optimise the chemistry to either be able to store lots of energy in it, you know, the number of ions you can get in it, the power, which is how quickly you can get the ions in and out. Interestingly, you know, a very simple way to think about it is in an energy cell where you want to be able to put lots of energy in it, you tend to pack the molecules really tight so you can get lots of ions in, but those, because it's packed tight, those ions can only get through that lattice really quite slowly. If there's any chemists in the room, please excuse me. And then, so the fact it's an energy cell means that the ions take a long time to find their way through because it's, you know, it's so dense. And then in a power cell, which you need if you want to get loads of energy in and out quickly, tends to be a lot more open so that they can get in and out. But obviously you can't pack as many in. So you know, I always think with physics, you know, you get one advantage, it takes something away somewhere else. There's never one simple solution.
Sod's law applies.
Yeah.
Yeah.
So would you have some of each in a battery? So some for performance and some for...
That's you've got to be careful with balancing the cells. There are solutions that look at that kind of thing, but obviously if it might mean that you work one cell harder than another, and that cell could be damaged, wear out, etc. Wear out's probably the wrong word, but age. You could overheat certain cells, so you have to manage all that. But they certainly do pair up different solutions. So you might have an energy pack with a supercapacitor. So supercapacitors are absolutely rubbish at storing lots and lots of energy, but you can get energy in really quickly. I always think of a supercapacitor, by the way, like a flywheel. It's a similar sort of thing. You can spin it up really quickly and get load energy out really quickly, but you can't store a load of stuff in there. And what you do store in there won't stay in there very long if it depletes over time. So it's not somewhere you want to leave energy or anything usable.
Can I ask a question just about the thing? What about accidents then? What about penetration of the cells? How do you handle the safety aspects of that? Physical damage to the cells, to the battery?
Yeah, so it's a fundamental, certain chemistries, lithium ion for one, it's a fundamental problem. So it's if it starts to burn, it'll carry on burning. So you'll want to physically protect it. You'll want to slow it down. There's a reason you can't take huge numbers of lithium-ion batteries on a plane, for instance. So the chemistry is such that it's got the fuel and the oxygen there. Even if you were to take all the oxygen away, it will still burn. It will keep burning. So you've got to let it burn out once it starts. So you have to monitor the cells, see what's happening, and then you'd have to warn the driver. So once something's penetrated it, it will go.
The infamous burning laptop phenomenon, yeah.
Yeah, all you can do is manage it as best you can.
How much does a 40 kilowatt hour battery weigh?
Car battery, yeah.
40 kilowatt hour battery, so that's, I think, the Leaf battery is just a bit smaller than that, that's 300 kilograms. But it's
significant weight penalty.
The thing about at a pure level, the active chemistry, if you were to just look at the active chemistry, 40 kilowatts wouldn't weigh anything like that. Problem is that half of the mass of the battery and it is not active chemistry. It's mechanical parts holding the cells. It's cooling. It's electrical contactors that have to open and close. It's buzz bars, metal buzz bars to take the energy around inside.
And presumably protective container.
And an enclosure,
How do you cool it? Is there a water circuit or what?
Various ways. So Leaf battery is passively cooled effectively, so you don't work it, the Leaf battery doesn't get worked very hard, so it does limit its capability, but effectively the cells, there's a cooling plate at the bottom and they use passive cooling to take that away. Others use heat exchangers. You can put fluid through them. Obviously you don't want that, they can use different kinds of fluid. Some of that fluid you don't want to get into the electrics. It causes you an issue. They are looking at different cooling fluids that don't cause a problem. But and that affects your energy density as well, so how closely you can pack the cells, because if you pack them too closely and they generate heat, you can't get it out. But a lot of the times those cells and modules you'll have, they'll have temperature sensors on them, so you can monitor if a cell's starting to get too hot. So then you'll stop it charging, you'll limit the current to protect against the a battery overheating and actually catching.
So the
fire.
actual control system's quite complicated, isn't it?
It has to be, because inherently the chemistry is, let's say, hazardous rather than dangerous. So it's a secondary protection system, if you like, that's managing that hazard, and your mechanical enclosure is containing that hazard rather than the chemistry as its inherent issues.
Probably not as dangerous as if a tank of petrol catches fire, to be fair. People do overdo this a bit.
It depends. If you've seen one go up quickly, it can be like a bomb.
It can destroy the vehicle.
And you've got noxious fumes as well, haven't you?
You've got some quite nasty fumes that can come out, yes.
Oh, from a fire incident, not normal operation.
There's a lot of talk about the future use of battery technology, but there isn't much thought or consideration that I'm aware of as to the reuse or the recycling at end of life. Can you give feedback on that?
Yeah, so, in the early days, you're absolutely right. So, bits were glued together, really difficult to take them apart, makes recycling really difficult. But now, any battery design in the last 5-6 years, probably 10 years to be honest, is designed to be taken apart, because the manufacturers are responsible, as an automotive manufacturer, you're responsible for end of life. So you've got to be able to disassemble it and recycle it. So that's a requirement. So that's got better. So we do a lot of work here. Actually, we've got a second life centre over the back over there. We also look at how you can take the material out if you wanted to. The best ways of extracting that material so you can reuse it. But actually, the most efficient way is to reuse the battery as a whole, put it into a second life, which can be some sort of local store. So, battery, it might not be any use in automotive when it's got down to like 60% of its capacity. It's still pretty,
Could I just comment on this issue?
Really
The critical issue, why a battery ceases to be of use in an electric car, is its energy density drops too low relative to the tiny space you have on the vehicle. Now, if you want to then take that same battery that's now no longer energy dense enough to use in a car and use it to back up the grid, which everybody says is terribly expensive if you buy new batteries, you now no longer have a size or weight penalty. You can have a big shed very, very cheaply and just spread them all out in a row. So they then continue to have a further life for maybe, I don't know, several years.
18 years.
There you go, thank you. Running at about half the energy density. So, and big companies like ABB, looking to back up the power grid, are already starting joint venture companies to do precisely that.
I understand that, but I think the question's still there.
So the question's still there. What happens at the end of that? Absolutely. The recyclability, quite so, yeah.
Faraday Challenge is actually doing a lot. I actually wrote a project which was second life for the batteries, remanufacturing, repurposing, recycling, and say Phil WMG's doing a lot as well. And there is
very good.
It's not so well known. What's interesting is everyone actually asks that question, and they only ask it about batteries. They don't ask about motors or anything else. No one thinks about anything else that's going in an electric vehicle. No one asks about hydrogen fuel cells. Everyone asks about batteries. Because that's all we care about right now. But as Phil said, the legislation also, there's the batteries directive as well. And because what's happening is people, when I talk to a recycling company, and they take, there's only like 7 in the UK that take them, the batteries all get sent abroad. But a car dealer phoned them up and said, someone's just part exchanged their car, can I sell you the battery? And he went, actually, you can pay me for the battery. And he went, I'll just put it in the corner and try and sell it at auction. And that's why everyone cares so much, because it will cost you lots of money. But I think if you ask him probably a year's time or 2 years' time, there'll probably be a very different answer and you'll see stuff. And it's that what's clear, and I keep finding out, is that, and I work in electrification as well, is that the wider public is not hearing anything. It's a common question that I ask again, but if someone's working within it, they can say, actually there's quite a lot of money being spent on research, but no one else knows anything about it, do they? It's
back to our wretched British press again, not reporting technology properly.
Yeah.
I'm coming back to supply again. What are the main ingredients of your batteries? Lithium is one, but are there any other materials?
Lots. I'm not a chemist. So.
Where do they come from?
Cobalt's critical, isn't it? I'm not quite sure what for.
Also, which obviously depends what you make the anode and cathode out of. I'm probably the wrong person to ask, to be honest, because I'm an electrical engineer rather than a chemist. But there's various bits and pieces in there.
Cobalt's the one everyone talks about, is because it's from, most of it is from the Democratic Republic of Congo.
Yeah.
So it's a conflict material.
Blood cobalt, yes.
Cobalt, nickel, I mean, there's actually a lot of battery recycling goes on. I mean, all lithium-ion batteries by law have to be recycled.
Oh, didn't know that.
It's a batteries directive, so that's why, you know, when you go to a supermarket and they have a batteries collection thing,
Yeah.
if you're a company with over a certain number of employees, I think it's a revenue, you must collect and take back any batteries that you sold. It's producer responsibility legislation.
Oh,
All
yeah,
the
yeah.
big supermarkets just take all of them, because otherwise you have to prove you bought them from them. And that same legislation applies to the battery in a car. Is actually an industrial battery. It's not, the automotive is the one that starts it, but it's an industrial battery. And by law, they can't be landfilled. Which actually applies to any waste.
That's good.
So they have to be recycled.
Makes a nice change. The government's legislating properly.
Like we import all the materials right now. All batteries right now, lithium-ion batteries are shipped outside of the UK for recycling, mainly to France and Germany, I think, and Switzerland, Belgium. Belgium's got a very big one, so they're all shipped out there. And they basically burn them and recover, you know, some of the fractions. Again, I'm not a chemist either.
They put them in a big shredder.
Yeah, they shred them.
They shred them, and they in a lot of cases,
yeah.
and then you can use that to extract all the different components.
Pyrometallurgy, and I wrote a report, so I know a little bit, but I don't understand it. But no one really recovers lithium, again, because it's not financially, doesn't make sense. So
It's low value, isn't it? Yeah, sure.
It's not breeze blocks.
It's the precious metals they need. Yeah.
Yeah, they make. I mean, but still, you pay to have that done because the business is there because you by law have to have it recycled. That's what it says. European legislation that's in UK law as well. But financially, it doesn't really make sense otherwise. So you pay for it.
Yeah.
So it's a strange business model.
May I ask about electric motor technology in the automotive field? Are there many people using these pancake motors in yours yet?
Not a lot is the answer, and the reason is you can fit one motor in a central part, a central unit. So I think you've got to think about where automotive has come from, and there are very, very few cars that have been designed from the ground up to be electric. So what they've actually got is a car, and they've modified it, and you've already got a mechanical connection, so at that point is where you probably fit the motor. There are a few more and more, if you like, axle motors, people putting motors in the axles, but the problem is with putting a motor in a hub motor effectively, is it's unsprung mass as well. And unsprung mass is not good for drive, handling, and all sorts of horrible things. So that tends to be why not. But then, you know, there are...
It's about removing the drivetrain, you know.
Yeah.
It just seems a sensible solution. If it's not in the actual sprung mass, it's just driven on a short axle.
Yeah.
It just seems sensible to me that why haven't we gone down this route? You could have 4 small motors, you know, in a...
But if they're small motors, they're not powerful, are they?
Well, what I'm saying is...
No, 4 small with the same power as one big one.
Yeah, quarter of the size of the big one.
But as a general engineering principle, 4 small motors will cost you significantly more than a single one of 4 times.
It's still heavy.
Yeah. Oh, you're not saving weight, sure.
Multi-kilowatt motors.
But you're spreading it nicely around the vehicle.
Yeah, you're spreading it.
Logical way of putting power to the wheels.
But it is unsprung weight.
You've got to have a very flexible electrical connection as well.
Oh, that's not too much of a pump.
It just seems logical.
Can I just ask? Oh, sorry.
Just to answer the question. So, again, when we were first looking at various architectures, we considered everything, and we costed up everything, and we looked at the benefits of everything, and you've got to look at all the attributes, and not just cost, but also the ride and handling, packaging, what it means from tearing up the car. You've got to redesign the suspension because you've changed the weight in there. Then it becomes a problem. You've also got to cool it, so it's not just an electrical connection. You need coolant because the motor's it's 95%, 90% efficient. That's still 10% of heat it's going to make, which you've got to get rid of. So there's other things that come into it. When you consider it as a whole, I think if you were designing a vehicle from the ground up, then it makes more sense. But Tesla's got 2 motors front and rear. Is the way they've done it. Rather than put an axle on motor into making it 2 axle motors. But that kind of works. It's kind of halfway out.
Can I just ask 2 questions? One about buses and one about heavy trucks. Let's do the heavy trucks one first because it's easier. I'm of the school that says you can't build an electric HGV because the battery for the sort of typical HGV range would take up the entire truck. Yeah. But Tesla have unveiled this electric truck, so what's the secret? Is it actually only got a very short range?
If you were to do the calculations, it would make sense.
Yeah, good.
Makes sense. But
okay. So it's a bit of a stunt.
Yeah.
Okay.
As I said, they are talking about trucks with effectively, like a electrified railway.
Well, that's what I was going to ask next.
Yeah.
For urban transport on a defined street pattern, on defined routes, we used to have a perfectly good solution for this that was called the trolley bus. We can all remember them operating in the 1960s. I don't understand why they haven't come back, given that there's no weight penalty of batteries and no cost of a battery. If you could help explain to us why they haven't come back, in your opinion, that would be interesting, because it seems to me they're a much more obvious solution than a battery electric bus. On fixed routes, of course, obviously, yes. But my other question was, you briefly mentioned the bumper car idea. We're all used to these Dodgem cars running around with this grid overhead. It's always been my favourite fantasy. You could electrify a motorway that way. So can you tell us what some of the practical problems are and why it's not being done?
For the same reason, to be honest, why they haven't managed to electrify a lot of the railway network, is it's
just high capital cost.
It's massive cost. It's infrastructure cost. So if there's a simpler way of doing it, but you've got to put pylons. It's not cheap.
Well,
the aesthetics of the trolley buses in an urban area, I should imagine these days. People just don't like.
You think that's a serious issue? What, for planning approval?
Yeah.
I'm surprised. I mean, there weren't big beefy gantries like you have on an electric railway, and they were quite flimsy structures.
Well, why not put them in the road?
Yeah. Maybe it's to do with property ownership rights that people don't like having them attached to their buildings, aren't they?
There's some around, but
very few.
Again, it's investment in infrastructure. I don't think personal opinion. Nothing to do with WH for me. So we used to have buses that were regulated and deregulated. There's a lot less control. The local authorities, the people that are in charge of it, I don't think they've got the budgets to do a lot of these projects.
Oh, they just don't have capex budget, sure,
Yeah, and
they're not allowed to invest.
I've done some work with some bus operators and bus companies. And when you do all these cost calculations for running costs, you think, well, we're getting somewhere, you think we're getting close. And then they pop up, well, we don't pay any tax on our fuel. So, and that's the thing. It pulls the rug straight out of any business case.
Right.
Because their running costs for
they're tax-free on their liquid fuels.
Are so cheap. Which you look at how dirty some of these buses are.
Yeah, very.
And those buses have run. There's a lot of buses in operation that are 10, 20 years old.
Oh, at least, and the rest. All the 30-year-olds around.
They've got that old level of emission control as well. So that there's huge opportunity, but I don't think there's the investment.
So going back to the marine applications and the Norwegian Ferry, are you aware of the battery technology that is actually installed on that vessel?
I don't think it's anything particularly clever. It's a standard lithium ion. I don't know whether they're pouch or cylindrical cells, but I don't think there's any Anything particularly clever in the chemistry?
Just lots of them.
Yeah.
Because taking that a step forward, it's almost like the issue of, in this discussion, everyone's been concentrating on advanced battery technology, whereas for marine applications, the power to weight ratio densities, that need isn't necessarily there.
Yeah, indeed,
So,
nothing like as severe as
again,
automotive.
Considering what is actually in service in marine environments, considering submarines and conventional submarines, the battery technology is, if you say 60s technology, is probably being very positive about it. So I don't know if your calculations took that into consideration when looking at an intermediate system for a ship.
Yeah.
I think the safety issue is a big one though. The latest nuclear submarines still got standard lead acid accumulators purely because of safety.
Oh.
They wouldn't consider lithium ion.
The Dutch have gone.
Have they?
Yeah.
Well, our Navy won't consider it.
But again, it's about battery density and power density issues and related to cost. Whereas those issues are important in marine applications, but haven't got the same massive, I was going to say driver, that's probably the wrong word to use with the automotive industry. And again, just taking as an example, remembering back to the container ship, a standard 50 megawatt diesel engine weighs about 1,800 tonnes. And we looked at a comparison with the gas turbine application, where the gas turbine itself weighed 26 tonnes. And looking at the cost differentials in terms of extra cargo carried and that type of thing. So those sort of considerations perhaps need to be taken with the electric side.
Yeah, you do.
The lithium-ion type batteries are, if I'd suggest a bit of a red herring, I think that's the case.
Well, I'll cover two things. So, a lot of the cost in the battery pack in an automotive, as I say, only about half of that is the actual chemistry, and there's all these other components in there, and how dense you pack them. If you don't pack them densely, they'll cool themselves. If you don't work them too hard, they'll cool themselves. You're just not making very much use of the space. So you can take the same cell that's being produced by the million, if you like. So you can take the 18650 Tesla cell, which in a Tesla is packed really densely and nicely cooled and everything. You can spread that out, and you could use the same chemistry. It's not just the chemistry; it's the mechanical module itself. And sort of give you an example. So when I moved from automotive, I moved into to JCB, which is a construction company, and I was always used to weight being absolutely the most important thing. Probably not as much as it would if I was working in aerospace, but pretty damn important in a car. And then with JCB, with a construction machine, which would normally have a great big counterweight on it to stop it falling over when it's picked something up. Actually, the problem becomes that the battery, if you take the counterweight off, the battery weight density isn't weight dense enough for the same volume. You still need to put counterweights on. So weight, just don't worry about weight. Worry about the fact that you're taking up a volume where you could be putting weight, that sort of thing. But you've got to look at the whole picture.
I've got a question on battery energy density. That's in the topic at the moment. Where are we on current battery density in terms of watt hours per litre? And where do you think that will be going in the future? And what's your opinion on 3D and solid state batteries?
Again, I'll say I'm not a chemist, but I think solid state have got a lot going for them. Safety is one. Safety is going to be one of the big drivers of solid state batteries. Where we're going to go, I can't remember the figures, but the Automotive Council sets out some figures to between now and 2035, and we've actually, the previous sets of figures, we've actually, nobody ever thought we'd get, realistically $250 per kilowatt hour. Actually, we achieved that earlier than the original plan. But energy density, power density, I can't remember the figures, but they're looking at just about doubling that, I think, by 2035. And energy, power density also comes into motors, by the way. So again, I can't remember the figures off the top of my head, but again, they're looking at technologies to get us double the power density of the motor as well.
I've read some articles in the press, and they reckon we'll achieve the doubling to about 400 watt-hours per litre, I think, within the next 5 years. I was just curious to think that's realistic or not.
Yes, but it's, again, not just down to chemistry, it's down to clever cooling, it's about the other things you can do. Because if you open a battery up, a battery pack up, you'll see so much of that is not active chemistry. So it's being cleverer.
And what's the motor technology you use in cars?
You speak up.
Yeah, what's the motor technology being used at the moment?
There's not one. So permanent magnets, induction motors. So Tesla's got some induction motors on it, which is not the top end of technology. Not having, I mean, a lot of manufacturers are looking at moving away from permanent magnet machines, so they don't have to go and get permanent magnets from the one place in the world where they're available, because they're becoming a bit like diamonds. They can control the market. It's not that there's a shortage of permanent magnets. It's just that they come from maybe certain areas in the world.
It's a monopoly supplier.
Yeah. But being able to move away from them is something we're considering. Because it doesn't make sense, if you're thinking of security of supply of your fuel, it doesn't make sense to move to something else that's just as problematic.
Yeah.
But yeah, there's lots of different motor technology, and it's the appropriate one. And a lot of it depends on how much space you've got, whether you need, how much torque you need, what you can fit in the space, how much you need to cool it. So, induction motors are generally, you can throw anything at them, they're cheap, they're not going to give you the best power and power density, but if you've got the space, they can be ideal because they're cheap.
Yeah. Okay, we're going to have to stop there, I'm afraid. Phil, thank you very much. Very enlightening for us amateurs who don't really have any experience of this area, but you've covered a lot of ground, and you've given some good insights into the problems, particularly as they might affect ships. There are already environmentally controlled areas in littoral areas in Europe and the States and Canada. So it's coming, the legislative pressure is coming. It's already fairly strong and costing quite a lot of money, but it's all pushing in that direction to perhaps hybrid, and as Paul pointed out, maybe an answer is electric tugs. But certainly I think Britain is somewhat behind other countries in doing something about the problem, and I think the pressure is definitely increasing. So thank you very much for a very interesting and informative lecture. Very good value. You've had a very good audience for us anyway, and some good questions and very good answers. Thank you very much.